In the name of God, I'll present the paper entitled Android Malware Detection Using Supervised Deep Graph Representation Learning. First, I'll briefly talk about the basic concepts and then I'll present the proposed technique and the experimental results. Malware is a program intentionally designed to harm computer systems or gain illegal access to them. Android is an open source and Linux-based operating system for mobile devices, leading the market with more than 70% market share in August 2022. The popularity of Android along with openness has made it an attractive target for malware authors. Deep learning is a powerful machine learning technique in different domains. The multi-layer structure of deep learning models allows them to deal with high-dimensional data. In recent years, research focusing on deep learning for malware detection has received more attention. Graph neural networks or GNNs are a flexible and powerful class of deep learning models which are directly applied to graph-structured data. GNNs use a message passing scheme in which each node iteratively receives messages from all its neighbors and aggregates them to obtain its new state. GNNs capture the complex dependencies of the graph structure's data through this iterative process. Since executable programs or Android applications can be represented in various graph structures, GNNs could achieve a good performance in the malware detection domain. Deep learning is feasible to learn higher-level concepts based on local feature representations. Autoencoders are one of the most common deep feature learning techniques. They learn efficient low-dimensional representation of high-dimensional data. An autoencoder consists of two parts, an encoder and a decoder. The encoder compresses the input into a compact and meaningful latent representation, and the decoder takes the latent representation and tries to reconstruct the input as similar as possible to the original one. In this paper, we combine autoencoders with GNNs in a unified way and present a novel architecture for deep graph representation learning in a supervised manner. More specifically, in this paper, we present DroidMalGNN, an end-to-end deep learning technique for Android malware detection. DroidMalGNN uses autoencoders for deep graph representation learning and separately trains two autoencoders with graph convolutional layers. One of these autoencoders is trained with benign and the other is trained with malicious Android applications. By doing so, DroidMalGNN can make a good difference in representing the embedding vectors of benign and malicious Android applications for classification. DroidMalGNN first extracts an attribute function called graph_fcg for each Android application. Nodes in each fcg represents internal or API functions. The feature vector of each API node is obtained by applying one-hot encoding to its corresponding function name, and all non-API nodes are assigned the same one-hot encoded feature vector. We consider API functions commonly used by Android malware for malicious purposes as critical and prone each FCG to leave only nodes with at least one critical ancestor. In the deep graph representation learning step, we train two autoencoders with benign and malicious FCGs separately, each of which consists of multiple graph convolutional layers and learns the latent representation of its input FCGs by reconstructing their feature matrix. The graph convolutional layers are recursively defined as this relation. In this relation, I tilde is the adjacency matrix with added self-loops. D tilde is the diagonal matrix of A tilde. W is the trainable weight matrix. F is the activation function. And Z is the output. The output of each layer is fed to the next layer, and the input of the first layer is the feature matrix X. In each autoencoder, the graph convolutional layers of the decoder part are arranged in reverse order of the encoder part. The latent representation is represented by y, and the reconstruction loss is defined in such a way that the reconstructed feature matrix has the minimum distance from the original feature matrix. In the malware detection step, we first feed each FCG into both benign and malware autoencoders and extract two latent representations, and then apply a mean pooling layer to each latent representation to compute the average of all its node embedding vectors. We obtain a dual embedding vector for each FCG by concatenating these two obtained embedding vectors together. After generating the dual embedding vectors of all FCGs, we use them to train an MLP classifier. As you can see in this figure, each FCG is given to both benign and malware autoencoder after extracting two latent representations and applying mean pooling layers. A dual embedding vector is obtained by concatenating these two obtained embedding vectors together. Finally, an MLP classifier is trained, which is followed by a softmax layer to decide whether the application is malicious or benign. The dataset and basic experimental setting used in the experiments are shown in the slide. This table shows the impact of the number of graph convolutional layers. As can be seen, the autoencoders with 6 graph convolutional layers, the autoencoders with 6 graph convolutional layers can provide a better trade-off among different evaluation measures while keeping the false alarm rate at about 1%. This setting can achieve a detection rate higher than 94% and an accuracy of about 98%. This table shows the impact of the number of hidden layers. We observed that the MLP classifier with two hidden layers can provide a suitable trade-off among different evaluation measures. In this figure, we compare DroidMalGNN with a baseline model called JMLP, which have an autoencoder for deep graph representation learning instead of two benign and malware autoencoders. The results show that DroidMalGNN can fit more discriminative embedding vectors into MLP classifier. This figure compares the loss of benign and malware autoencoders for benign and malicious FCGs. We observed that the benign autoencoders produces less loss for benign FCGs than for malicious ones, and the malware autoencoder produces less loss for malicious FCGs than for benign ones. In this paper, we have presented DroidMalGNN and Android malware detection technique that utilizes deep graph representation learning in a supervised manner. It combines the autoencoder architecture with GNNs and separately trains a benign and a malware autoencoder to generate a dual embedding vector for each given FCG. A dense neural network follows the proposed deep graph representation learning architecture to learn a malware classifier. Experimental results have shown that DroidMalGNN can achieve good detection performance. Thank you for your attention.